So this is the first proper lecture for the course 327, Geometric Topology. And most of the first half of the semester we'll be talking about knots and their classification and invariance. But first I need to cover some matters topological. Now if you took metric spaces and topology, you should know everything I'm going to say in this video segment. Maybe this will be a review for you. If you haven't done that course, that module, you'll probably need to do some reading to properly understand what I'm saying today. And you can either look in the lecture notes for that module, which are on Keats, or you can look in the chapter in the book by Gilbert and Porter, a copy of which you can probably find somehow online. So here are the key facts that we'll need regarding topology and topological spaces. But I wouldn't worry too much about this because we'll be working in three-dimensional space and the plane, so most of the things should be fairly obvious. But one does need a bit of topological background to fully understand the statements of certain theorems. So I'm just going to go quickly through as a sort of summary. So a topological space, the idea is we take the sort of things we're familiar with, like ordinary Euclidean space, and we abstract certain concepts. We don't really need the idea of distance. So anyway, a topological space, therefore, is a set, any set, X, in which we distinguish a certain family of subsets. These are called the open sets, or the open subsets. And in order that this form a topological space, there are certain conditions which I haven't written down here, but you can easily find in any text. I'm going to tell you what they are verbally. So this family of subsets which you distinguish has to have certain properties. The first property is that both the whole set X and the empty set are open. They're declared always to be open. The other property, the second property, is that if you have two open sets, their intersection must be open. So it follows from that, if you have any finite collection of open subsets, their intersection is also open. And the third property is that if you have any collection of open sets, finite or infinite, their union is also open. So finite intersections of open sets are open, but arbitrary unions are open. So with those conditions, you've defined a topological space. Now, there are some obvious examples. You could take any set and take all possible subsets, including the empty set. That would be a topology. That would be a family of open sets which satisfies, obviously, the definitions I've just given you. But that wouldn't be useful in many situations. So to make the topology useful, one needs to restrict the open sets and have a sensible criterion for subsets to be open. So in ordinary Euclidean space, in particular in R3, when is a subset open? Well, it's open if around any point you can fit a small open, well, a small ball, let's say, in the usual sense of the word ball. If given any point, you can find a sphere and all the points inside that sphere belong to the subset. If that's true for all points of the subset, then the subset is open. So, for example, if you take a cube with its boundary faces, that is not open because that property does not work if you choose a point of the boundary. But if you take a cube and remove its boundary faces, what's left is an open subset of R3. So you can then easily prove that the properties I read out are satisfied. So that is the usual topology, the usual family of open sets in R3, and you can deal with the real line and the plane in a similar way. Okay. Now the point is, one reason for sort of taking this definition of topology and forgetting distances is that it makes it rather easier to do some of the sort of standard tricks in analysis, because you normally learn about continuity and definitions of when a function is continuous by using epsilons and deltas, but we can't really do that here because we don't have a concept of distance, or even in the real line. We don't want to really use the numerical concepts. And the point about the definition of a topological space, it's set up in order to define continuity very easily. A function is continuous, a function between two topological spaces, let's say from the real line to R3 or from R3 to R2 or whatever. Such a function is continuous if the inverse image of any open set in Y is open as a subset of X. Remember, X and Y are topological spaces, so by construction we've distinguished their open subsets, we've declared what their open subsets are, and we require that the inverse image of any open set in Y is open in X. So if V is open in Y, F inverse of V, that means all the points in X that map to V, that's an open subset of X. This is a definition, so I said if, but that's really if and only if, because that's the definition of continuity for arbitrary topological spaces. And it's easy to see that this will be the usual definition of continuity if X and Y are Euclidean spaces, in particular if X and Y are both the real line. So you see, that's a very neat definition, but it involves the inverse image. It's not true in general that the image of an open set is open, but the inverse image of an open set is open if the map is to be continuous. And then moving on, we want to know when two topological spaces are equivalent. And this is the notion of homeomorphism. So it's a funny word because it reminds you of homomorphism, which doesn't really mean equivalent in algebra. It's just a certain type of mapping. But homeomorphism in topology is an equivalence relation on topological spaces. It's really more akin to the word isomorphism. I don't know the history of this. It's sort of a bit confusing. But anyway, a mapping between two topological spaces is a homeomorphism. It's got to be bijective. Remember, X and Y are sets above anything else. So the mapping has got to be bijective. And it's got to be continuous, because when you talk about maps in a topological context, you always assume they're continuous. But we also have to impose that the inverse mapping, which exists as a mapping, because F is a bijection, the inverse mapping, F inverse, is also continuous. So now it is true that if U is an open set of X, then the image of U is open, because really that's the same thing as saying we're talking about F inverse of U. So a mapping is a homeomorphism if it really induces a bijection from the open subsets of X to the open subsets of Y. If U is open in X, if and only if its image is open in Y. That's a homeomorphism. Okay. Now, there's just a word of warning here. If you were doing something like linear algebra and you want to define isomorphism, it's sufficient to say that the map is linear and it's bijective, at least between finite dimensional vector spaces. Then the inverse mapping would be linear and bijective, so there's an inverse mapping, and the inverse mapping would automatically be linear. But for arbitrary topological spaces, even if it's continuous and bijective, the inverse mapping is not necessarily continuous. It is in many cases, but not in all cases. So you have to impose that in the definition. So homeomorphism simply means a bijective map between topological spaces, which is continuous and its inverse is continuous. So it's a good idea to try and think up examples. For example, try and write down a homeomorphism from the real line to itself that's not the identity mapping. It turns out you could even find a homeomorphism between the open interval 0, 1, the open-ended, both sides, open interval 0, 1 to the whole real numbers, because those two spaces are homeomorphic. Okay. Now, I've defined what it means for a set to be a topological space. You have to have this family of open subsets. It's very easy then to generate new topological spaces. For example, if you take any subset of a topological space, then that is automatically a topological space in its own right, with a definition induced from that of X. So you just say that a subset of S, so S is now a subset of X. X is a topological space. We don't know yet about S, but S is a topological space because you say that a subset of S is open if and only if it's the intersection of an open set in X with S. And that definition will satisfy the properties I mentioned earlier, and that is the so-called induced topology. In fact, I implicitly used that at the end of the last slide because I was talking about the interval 0, 1, the open interval 0, 1. Why is that a topological space? Well, it's a subset of the real numbers, so it gets this induced topology, which is also an open set in, well, it's an open subset of R, but it gets an induced topology itself. Another perhaps easier example to imagine geometrically is just the ordinary two-sphere. That means the set of unit vectors in R3. That's a subset of R3, so it becomes in its own right a topological space. And to say a set is open in the two-sphere simply means that you can surround that point in the two-sphere with a little disk, a little curved disk on the two-sphere. That's the definition of an open set on the two-sphere, because what you're really saying is that curved disk is the intersection of a ball in R3 with the two-sphere. So two-sphere is a topological space. In fact, it's an example of what's called a two-manifold, a surface, as I mentioned in the introductory lecture, the second introductory lecture, a surface or a two-manifold, because the neighbourhood of every point looks like the plane topologically. There's always a neighbourhood of each point which is homeomorphic to a disk in the plane. So that's the example of how you make any subset of a topological space in its own right. Now, a slightly more complicated definition, but one that's equally important, is that another way of inducing or finding new topological spaces is whenever you have an equivalence relation on a topological space. Any equivalence relation, so remind yourself of the definition of an equivalence relation if you don't know the three properties. An equivalence relation on a set is really the same thing as a disjoint of partitioning the set into disjoint unions, which are the equivalence classes. There may be infinitely many. It's a disjoint union that covers the whole set. That's really the same thing as an equivalence relation. And the set of those equivalence classes becomes a topological space in its own right. It acquires what's called the quotient topology. And the definition of that, I've got to define what does it mean for a subset of equivalence classes to be open. And the point is, whenever you have equivalence class, when you have an equivalence relation, you have a mapping pi, which maps the set to the set of equivalence classes. It just maps an element of the set X to the equivalence class that contains X. That mapping I call pi. And you want to declare a subset of the quotient of the set of equivalence classes to be open if and only if its inverse image under pi is open in the original topological space. That will in particular tell you that pi is a continuous mapping, which is what you want, but it gives you a topology. When I say topology, I just mean declaration of when a set is open on the quotient. Okay, now it's important to study some examples of that. I don't have time to give many today, but one classic example is to take a torus. That means the sort of donut-shaped surface in R3, but you can define it in a more abstract way. You can just take the plane and declare any 2 points in the plane to be equivalent if their coordinates differ by, if both coordinates, both x and y coordinates, differ by an integer. So what you've really done is you've sort of divided the plane up into lots of squares, and basically you only need the unit square, part of the unit square, to define any point on the torus, because if you translate by integers, you're going to get the same point. So in this case, you get an induced topology, you get a quotient topology, and it turns out that's the same topology you get. You can identify the space you get with a sort of ordinary donut-shaped torus as a subset of R3, but as a subset of R3, it also has its subspace topology, and these two topologies are the same. The set of open sets is actually the same. Perhaps a less familiar example is of a new space, if you haven't seen it before. You start with the ordinary two-sphere, and you declare 2 points on the two-sphere to be the same, to be sort of be equivalent, if they're antipodal, if they're opposite each other. So in other words, I'm just imposing an equivalence relation on the set of unit vectors by saying that any two unit vectors are equivalent if they're either the same or they just differ by multiplying by -1. So that means any vector is equivalent to minus itself. And that means we've really just taken all the points on the two-sphere, we've identified each point with its antipodal point. So it's quite hard to imagine the set you get that results from that, the set of equivalence classes. But whatever it is, it's called the real projective plane. And it acquires a topology from the definition on this slide. But I just want to finish really then with explaining a bit more about the real projective plane, how you can imagine that. No, well, I'm going to do that afterwards. Sorry, I've got to talk about connectedness and compactness. So there are lots of definitions that go along with certain types of topological spaces. But the two important ones, I think, or really the most important one for this course, would be the notion of connectedness. And that's very easy to imagine intuitively. But we can put it in the context of topological spaces, because we can simply say that a topological space X, when I say space, I mean a topological space, is connected if there's no proper subset, U, that means U is not all of X, such that U and X minus U are both open. So you cannot partition the set X, the space X, into two subsets which are both open. Partition means that I'm writing X as a disjoint union of U and its complement. We can never do that with both the U and its complement, both of them open. If we can do that, the space is said to be disconnected. Okay, now if you take the usual definition of the topology in the real line, then you can prove, it's not completely trivial, but you can prove that a subset of the real line is connected if and only if it's an interval. It could be an infinite, it could be the whole real line, of course, because by definition, the whole real line and the empty set, they're both open. Or it could be a half open, it could be a half infinite interval, or it could be a finite interval, which is either closed or open, or half closed or half open. All those are connected, and those are the only connected subsets of R, the real line. So that's the notion of being connected. If a set is not connected, then you can talk about its connected components. It's fairly obvious intuitively in the Euclidean case what's going on. Now, proving all these facts is a bit technical, but once you've done it, then the sort of analysis theorems become easier. For example, if X is connected, if X is a connected space and F is continuous, then the image of X has to be connected. Not like the open sets when it's the inverse image, but it goes the other way. If X is connected, then its image, F of X, is connected. Or if F is any map from X to Y, and we take a subset S of X, which is connected, then the image of that subset has to be connected. And that leads you to, you can interpret, if you take X and Y to be subsets of the real line, you can use this to prove the famous intermediate value theorem. If you have a continuous function, it can't sort of skip values. And that's because the image, if F is defined on an interval, the image of F has to be another interval, so it can't skip values. That is the intermediate value theorem. So that saves you all that technical proving of the intermediate value theorem. In practice, the technical stuff is hidden somewhere in these definitions, but it's neat to sort of say it using topological concepts. The other sort of capital C which you need to know about is a space being compact. This is a more technical notion, slightly harder to define it, but what it means is that the definition of compactness is that any open covering has to have a finite subcovering. So what that means is if you can describe X as a union of finite or infinitely many open sets, infinitely many open sets, then you can always extract a finite number of those open sets which still covers your space X, for which X is still in the union of that finitely many open sets. If that's the case, the space is called compact. But you don't really need this abstract definition in this course because we'll only be working with Euclidean spaces and their subsets. So in that context, the subset is compact if and only if it's both closed and bounded. Now, closed simply means that its complement is open, although you can also interpret closed in the usual sense of limit points. In the case of Rn, to say closed means that the subset contains all its limit points, but really the definition for today is that closed is just the complement of an open set. And the subset has to be bounded. If those two conditions are satisfied, and they have to be satisfied if the subset is compact, and vice versa, it's slightly harder. If those two conditions are satisfied, then the subset is compact. That's true when you're talking about subsets of Euclidean spaces, the so-called Heine-Borel theorem. So you can really think of compact for this module as meaning closed and bounded. So again, we have an analogous theorem. If X is compact and we have a continuous map from X to Y, then the image of X is also compact. So now if you take the special case of F mapping an interval into the real numbers, an interval AB, a closed interval AB to the real numbers, then first of all, the closed interval is closed and bounded. So A and B are finite numbers. So the closed interval AB is compact. And I've already said it's connected. So its image has to be both compact and connected. So its image has to be a closed interval. Putting all these facts together, which I'm telling you about but haven't proved, its image has to be a closed interval. So in particular, if the image is a closed interval, it means that F is bounded, and it also attains its bounds because there will be points F of something will equal C. So C is the maximum value of F, and C is F of something. So F attains its bounds. So it's a famous result from maybe first year analysis, second year analysis, I'm not sure. F is bound, a continuous map from a closed finite interval is a real valued function is bounded and the function attains its bounds. Okay. Now back, last slide for this first lecture. I wanted just to tell you something more geometrical. Okay, it's been all sort of abstract topology so far. Now let's do some geometry. I want to tell you a bit about this real projective plane. This is an example of a surface of a two-dimensional manifold. It's not an oriented surface. I mentioned oriented in the second introductory lecture, which I say more about this in the second half of the course. We will be concentrating more on oriented surfaces, but I think we should know about let's only know about the non-oriented ones, and this is the simplest non-orientable surface for two manifolds. So another way of defining this, I defined it from the two-sphere, but another way of defining this, perhaps more usual way of defining the projective plane, or you can adapt the definition to define any projective space, is that you take X to be R3 minus the origin, and you say that two vectors, two non-zero vectors in R3 are equivalent if one is a multiple of the other, if they're scalar multiples. So that means that the two vectors are lined up, and they may be same or opposite directions, but they're lined up. They may have different magnitudes, but as vectors they're in the same direction or in opposite directions. If that's the case, they're declared to be equivalent. Neither of them is zero, so this is completely symmetric operation. It's an equivalence relation, and the set of equivalence classes is the real projective plane. Or if you started with Rn plus 1, the set of equivalence classes will be the so-called n-dimensional projective space. So that's another way you can define the projective plane. I started with the two-sphere. Well, you could also just restrict this construction to the two-sphere. Then to say that two vectors are multiples, you don't have much choice, because if they already have unit norm, they're either equal, either u is equal to v or u is minus v. So that's the previous definition I gave. It's completely equivalent. So this gives us the real projective plane. You could also start with any field, actually, and define the projective space. You start, as I say, with Rn plus 1, or any field, any set of vectors on n plus 1 coordinates, with each coordinate in a field F. You can define the n-dimensional projective space. You could even take F to be a finite field, like the field with two elements, and you get a projective space which is actually a finite set. No, we won't be doing that in this module. So, how do you imagine the case of RP2? Well, as I said before, any point is represented by a unit vector in S2, but you have to bear in mind that plus or minus that vector defines the same point. So, RP2 is homeomorphic, well, it's only in bijective correspondence to S2, in which opposite points, antipodal points, are identified. If V is a unit vector, you think of that as the same vector as minus V. So rather than using the equivalence relation, I've used the action of Z2. Z2 is just the group given by multiplication by plus or minus 1. So what we're doing, we're looking at the two-sphere, the set of unit vectors, and we're allowing plus or minus 1, well, plus 1 doesn't do anything, minus 1 to multiply that. So we have the group of 1 and minus 1. That's a group that acts on the two-sphere. And we can use that group to say that any vector v is equivalent to minus v. Now, if you take the two-sphere, we're making just the ordinary two-sphere, like the surface of a football. We're saying that any point is really to be thought of as equivalent to its antipodal point. So we only really need one of those 2 points to define a point in RP2. So what we can do is we can take our football and we can just chop off the upper half and just look at the lower half of the football, or the southern hemisphere if it's the surface of a globe. So we just take the southern hemisphere, but we include the equator. And now you see we've almost got a complete one-to-one correspondence with points in the projective space, but there's still a slight problem, because if you're on the equator, you could still have 2 opposite points on the equator that really correspond to the same point. Now, if you just take the lower hemisphere with the equator, if you just look down from above, that's like looking at a disk. So it's actually just like looking at this disk here, this yellow disk which I've drawn here. So you can think I'm looking from above, and that is the lower hemisphere of our football, for example, but the blue curve is the equator. And we've got to remember that any point on the equator, for example, this point here, the centre of the cross, is the same point as this point opposite it. Those 2 red crosses, or the centre of the crosses, that represents the same point. So what we're simply doing to get the projective plane is to take this disk, this yellow disk, we're actually identifying the points, opposite points on the boundary. So that's why we sort of have the 2 arrows going the other way. So any point, we're taking this whole part of the boundary here, and that's being identified with the part below, but in the opposite direction. So a point on the left here gets identified with a point on the right. It's a bit hard to understand that. You can also do the same thing with a square if you prefer corners. Instead of just doing a semicircle, the semicircle corresponds to these 2 edges of the square here, and the lower semicircle corresponds to these 2 edges. So I've now got 4 arrows rather than 2, but they're sort of going in backward directions. So you can think of the real projective plane as corresponding to all the points on the inside, uniquely specified as the inside, but then on the boundary, you've got to bear in mind that any point on the boundary, this point here is the same point as the one I just crossed above. So, think of yourself as an insect in this, crawling around this space, this topological space. You can crawl you can crawl any way you like on the inside, but if you get near the boundary, think of it as a sort of playpen, you don't actually get stuck if you keep crawling upwards. All you do is come out here. Similarly, if you crawl towards this boundary here, in that direction, you'll find yourself coming out here. So there's no boundary. This space has no boundary because we've identified opposite edges. So this is really what we call a two-manifold. It's a surface has no boundary. Any point has a neighborhood that looks like a disk, because even if you're on this apparent boundary here, you can sort of look both ways, and you still find it in the space, because with its quotient topology, you've done this identification and you get a sensible topology. Okay, that's enough for this introductory talk on topology. If you haven't done metrics and topological spaces, try to read a bit about the definitions I mentioned today, starting with that of homeomorphism in the places I mentioned. And then there will be opportunities to ask me more about this, but I don't really want to spend much time in this module talking about these technical definitions, because I think you'll find when we start talking about knots, you'll sort of you'll get an understanding of what we need from these more abstract definitions. So the next lecture will be on knots, examples and the definition of a knot in 3 space. Thank you.